Hello everyone, this is David Cecchini and I'm going to walk you through a few concepts and a few examples on how to use Spark NLP pipelines. We're going to check how to create pipelines and how to create pipelines when using multimodal models inside your pipeline. So hope you are all back to the training so we can start. Um, So basically, in Spark NLP, we have three different types of pipelines. We can use the pipeline as the object in the library, where we can create custom stages. We can process all of the data that we want to process using all the capability of the Spark ecosystem. So the input for our pipeline is a Spark data frame. So this is usually done when you want to process the data from end to end. So we get the data in your data frame. Usually you have a text column, and then we apply all the stages that you set in your pipeline. And then at the end, we get the information out of it. So this pipeline is mostly used when we want to make full application of Spark and then gain all of those speed improvements that we can get by applying it in a distributed computer. So the next one is light pipelines. I think you saw some examples before, but usually it is used when we want to experiment, we want to get fast results, and we are not running our data in huge amounts of examples. So we want to run, let's say, for a single sentence or a very small number of sentences, then we can just pass it as a text or a string value in Python or a list of strings. So we don't need to create Spark data frames. We are not going to use Spark to process them. We'll just run it in one single machine. So we can get it without all of the extra sending to Spark and getting back from Spark that we will have to do when using the pipeline. So this is mostly used for experimentation or when you need fast inference for processing one sentence or one text at a time. So you can use light pipelines. And then we also have pre-trained pipelines. So we can download them from NLP Models Hub. Then if you are applying them to solve a very specific problem, you can just load them directly, and then usually you don't change any of the components, any of the stages of your pipeline. So you are only interested, say, in translating from one language to another. So all the required pipelines is already built on it. You can just apply it directly. You don't need to create all of the stages. It's all built for you in one single object. So it's easy to use. You can prepare your own pipelines and save them to solve specific problems or to extract specific information in your data. So let's say there is one pipeline that you use every day or that you very often use it. You can just save it as a pre-trained pipeline and then reload it without having to declare each of the stages separately and so on. So pipelines, they work in a very simple way. So you keep adding stages to the pipeline. So we usually start with a document assembler, which will create a notation object from your text. And then we can start adding as needed. So if you want to split into sentences, you can use the sentence detector. And then if you need to split into tokens, you use a tokenizer. And then you can also normalize it to remove unwanted text, or you can remove stop words, you can correct typos, and so on. You can apply any stages that you need. You can also add word embeddings to your pipeline, and then you can just create your own pipeline. So basically, what it does is at every stage, you will be creating a new column in your Spark data frame with the output of that stage. So the document assembler, it creates one column with document annotations. The sentence detector will create a new column with all the sentences annotations object in it. So and so on. So for every annotation, every new stage in your pipeline, you will always be creating one new column where you can analyze, you can extract, you can view what was created by that stage. And just a comment, of course, some stages, they will need one previous column as input, but there are also models that need more than one column as input. Let's say for the embeddings, you will need both the document annotation that has the full sentence and the full text, but also the tokens information to create the word embeddings. So different models and different stages, they will have different requirements for the input, and then they create one single column with whatever it creates as an output. So when we talk about LLMs in Spark NLP, as it was mentioned before, we can add them just as an extra stage in our pipeline. So we can add one stage for text summarization or for question answering, text generation, translation, classification, and so on. And then we can just use pre-trained models to work on that task. So if we are summarizing text, we can find, let's say, a Fluently 5 model or maybe a different model that will be pre-trained on text summarization data sets. So it can summarize texts that are given to them. So for that, you probably just need the document annotation, and then it will generate the summary of that text with the model output. So for when we talk about LLMs, we have those three types of architectures that we can have, especially when we are working. All of them they are based on a kind of transformers based models. So we have models that are encoder only models. So we can use them, let's say, to create embeddings. And of course, all of those architectures, then we can add an extra classification head on top of the encoder to create classification. Let's say we can have a BERT model that creates embeddings, but we can also have a BERT model for text classification or sequence classification or token classification on top of that. But those architectures, they are primarily encoder only architectures, and then you can add extra for specific tasks. Then we have encoder decoder architecture that will first encode the input into a vector representation of it, and then uses the decoder to perform something else. So it can perform summarization, or it can perform question answering, or it can generate text, and so on. And then we have the decoder only architecture that will not pass all your inputs into an encoder part of your model, but instead it will start generating your answers directly. So whatever you give in your model as input, it will keep processing for next token. So we just use the decoder part of the transformers architecture, and then we can start generating answers out of it. Other features that are specifically created for LLM applications that we have and we support are working with OpenAI. For example, we can add a stage in our pipelines that will query OpenAI models for something. So we can query it using the completions for getting answers from prompts, or we can also query it to get embeddings of documents that we can send to OpenAI application. and then we can use those models directly inside our pipeline. So let's say we have a data processing pipeline, and we want to use OpenAI embeddings to create representation of our documents so that we can store them in a vector DB. So we can just create a pipeline, process it using OpenAI embeddings, and then save the vectors to our vector DB. We also have an object called LLM loader that can download large language models that we train that are open sourced. And then we can also support quantization so that we can use lighter versions of the models and just load them directly. So this LLM loader works a little bit different than the other ones that are applied inside the pipeline. LLM loader, instead, you load the LLM and you can query it directly without creating pipelines. And then we have notebook examples that you can check in our workshop repository on how to work with those directly. We also have a few features that we can use when building RAG applications. So we can split documents similar on how LangChain does. So we can split it either by number of characters or for some other rules that we want to apply to the text. And then we can connect to LangChain to use our models inside LangChain or Haystack as well. So we have connectors that we can, if you are familiar with those tools like LangChain or Haystack, we have connectors that can be used to use our models from Spark NLP and work with LangChain or Haystack. And you can find the notebooks with examples on how to do that. And then all of those models that we talked before, we can have several objects and several annotators in our library that will represent all of that. So for the encoder models that I mentioned, we can have Albert, bird, coming bird, the bird does, this still bird, and so on. And all of those annotators, they have a few different annotators depending on what you want to do with them. So we can have a bird embeddings. So we can just say, I want to create embeddings using a pre-trained bird model. Or then we can have a bird sentence embeddings that will create sentence embeddings using a bird model, token classification, sequence classification, question answering, and zero-shot classification. So all of those are available in most of those different types of models. And then we have special cases for working with embeddings. So new models were designed specifically to create better representation of words or sentences, and we have a few of them also implemented in our library. So we have PGE models, E5, Elmo, Instructor, UAE, and Universal Sentence Encoder. So those special types of embedding models, they can create very good representation of tokens or sentences, and you can just add them to your pipeline as other embedding models. Then for sequence-to-sequence models, we can also think about the transformers. So we can use BART transformers and GPT-2 transformer, Gemma 2, and so on. We have newer annotators as well. So we also already support Gemma 3 and Phi 3, and 25, and so on. So we have all of those annotators that you can use directly in the pipeline. And in the last column, we have healthcare specific annotators that you can also check on how to use them in the pipeline. So we have a medical BERT for sequence classification. So this is a BERT model trained on clinical data for sequence classification, so text classification. In this case, we have medical BERT for token classification, which is again a BERT model trained on clinical data to classify tokens. So let's say named entity recognition, and so on. We have a medical summarizer, medical text generator. So we have all of those models that were fine-tuned or trained from scratch in healthcare data sets, both open sourced ones and our own private data sets from John Snow Labs. So this is the introduction that I wanted to give, and then we can start checking code to see how to apply that into our pipelines. So first of all, let me zoom in a bit so you can see better the code. So basically, when you are working with licensed models, you need to have your license key. So I already uploaded my license key here in this environment, and then I can just paste my OpenAI API key. I can get it. You can get it from your account. Then we will set it in our Spark session so that we can use OpenAI calls inside our pipelines. The next one, we are going to install everything that we are going to work. So we are going to install LangChain, we're going to install John Snow Labs library, and we are going to install OpenAI and Face just to have a VectorDB in memory just for testing. So we installed everything. I already ran those, so I can start my Spark session. I think my session is already started, so I can check it. If I have it running here, this notebook and the other ones that are going to see today, we recommend using GPU if you have available, or if Colab gives you access to the free TPU or other GPU runtime. So this time I was not given GPU. We are going to run CPU for the moment. So I have a Spark session created. I'm running Spark Healthcare and Spark NLP on this session. So the first thing, let's experiment with open source or out-of-the-box large language models. We can start with simpler models like T5 or Flan T5 models. They are not as big as those big large language models that we have today, so that we can run them fairly fast in our notebooks for experimentation. But the pipeline that we're going to create, it runs very similarly with other models. It's just that the T5, which was the first model to start having instruction prompts, so they were the beginning of what we are now seeing everyday prompts. It was trained on different tasks in just one model. So we have different instruction prompts in our input to the model, and then the model will perform the task it is given based on those instruction prompts. So let's say we are summarizing text, we give the instruction prompt summarize, and then we send the text, and then the model will know that what it needs to do is summarize the given text. Another possible instruction prompt is to give a question, and then we can give a context so that the model will try to answer the question based on the context that it was given for him. So let's say this is an open book question answering task. Open book because it means you give the context and the answer should be inside the context. It's like reading a book and finding the answer for your question. So you can check all the resources that we have. You can read the paper on the T5 model. You can read the paper on the Flan T5 model to see what are the improvements on T5 given by the authors. They were from Google. And also you can also check our own notebooks on how to use T5 on different tasks and how to prepare data for all the possible instruction prompts that the model supports. So here you have a diagram on saying that one model, let's say a T5 model or Flan T5 model, was trained to perform different tasks just with one model. So this was different from what we were seeing before in the area where you have one model that does one specific task. So let's say one model that classifies, one model that will classify a token, let's say. But now we can perform many different tasks with just one model. So let's see, for example, open book question. So I already said open book question means that we give a context and then we give a question and we want the model to use the context to answer the question. In contrast, a closed book question would be, I only give you the question and you need to answer the question based on the knowledge that you have by yourself. So without consulting any extra material, without checking the context, you have to just answer based on what you know about the words. So first, let's see how to create all of that in a pipeline. We start with a document assembler. We will transform the text that will be given to the pipeline into document annotations, and then we can use a pre-trained model T5 base to answer questions. So we can set the task to question. So this will add a question to the input text before running the model. So while the model is being downloaded, we can check first how to prepare the data to answer closed book questions. So this means that the model, they will reply the questions with the knowledge that it has. And of course, those models, they were released in 2019 or 2022, so that the knowledge that they have is from that time. So it will not have any updated knowledge after 2019, for example. So when we are making questions, so this is a closed book question, so we are not giving context. So if we ask who is the president of the US, the model will reply with the knowledge that it has on the training data, so up to 2019. So we are going to pass a few questions, and then we are going to ask the model to answer them. So we can just create a Spark data frame with the questions that we have, and then we can just transform the data frame using the model to get the answer. So let's see how the model answers to the president of the US, most common language in Peru, and what is the capital of Germany. So of course, a few of the answers, they will not change with time, or at least they are not expected to change. Let's say the capital of Germany or the language that it is spoken in Peru, but the president may change after a few years, right? Every new election, you can change the president in a country. So this answer, it will depend on what year you are and what was the information given to the model at that time. Okay, so the model was already downloaded. We can run it and get the answers. So you see, the model answers for the president of the US. He says Donald Trump, most probably because this was the information given when the model was trained back in 2019. So, but the other questions, and of course, those are simple questions. So they just need basic geography knowledge, and you see that the model do have that knowledge inside it. So he knows that in Peru, they speak Spanish, and they know that capital of Germany is Berlin. So this is how you can apply question answering directly in your texts or using the model directly. So you can just ask the model for questions. Of course, this model is quite old, so it will not give you very good answers as new models that we have today, but still, this was a very important improvement in the machine learning community at that time. Next, we can see how to prepare data for open book questions. So we can have a context. So let's say an introduction to Spark NLP. We have lots of pre-trained models. We have lots of language present in the library. And then we have a very small introduction to Spark NLP here as context. So we may want to ask a few questions. So let's say first question is, what is Spark NLP, or how many languages are supported in Spark NLP? Can I use Spark NLP to scale my NLP application? So we can make all of those questions, and then we prepare the data frame like this. We will have the question, and then we will have the question plus context in the second column. So we will have one column containing the question and one column containing the question plus context as it is needed by the model. So then we can just create, use the model. So the model will receive what is question, what is Spark NLP, context, all of this text that we have here over here. So this is the input to the model, and then we can get answers. What is Spark NLP? It's a natural language processing library, which is something that is written inside the text. So it tries to find the answer in the context and then extract that to reply your question. So it's not creating a new information from his internal knowledge. Is just trying to get answer out of that context. So this was the first way of trying to avoid hallucinations, or trying to avoid to have wrong output in your model. So you can train models to reply to any type of questions, but you can give context. So how you get the context is a different question. So to automate solutions with that, you need to first know where the context, which context to give your model for each question, right? But this is how it was being done at the time. So this is naturally how it evolved for RAG applications. So we can try to create clever ways of getting context and then ask the model to retrieve the answer from that context. So this was already a problem that we have back in 2019. So you can also see that the model was able to find how many languages we have. So we have questions that the answers were present in the context. So the model was able to find the correct answer for it. So this is open book question answering that the model can perform. So you can see the model, of course, if you try to make it much more complex than that, the model will have a harder time to answer, because it's not as big as GPT models that we have today. So it's still in the millions of parameters at that time. And right now we have billions of parameters, which is much bigger models today. So the next section of the notebook, I'm not going to run it because it demands a much more stronger computer to run it, and I don't have that in Colab right now. I'm almost using all of the RAM systems I have available, but I want to show you how to use healthcare related large language models, so we can have small language models like for specific tasks that we can use. So let's say you are classifying text, you don't need a very big model just to classify a text. We can just have a specialized model for that with much less parameters. It can run much faster, and it can improve all of your processing pipeline. The same for token classification. So let's say we want to we are only interested in named entity recognition, so we can have a specialized model for that instead of having a very big and generic model that can do that but will be much slower and demand much more computer power. So let's see how to do that. We also have the quantized large language models that I mentioned before that we can use LLM loader to run them. So first, let's see an example for text summarization. So I'm not going to run it at this time. We can just create a document assembler. So we will transform text into document annotations. Then we can apply the summarizer on top of that to get the summaries of our document. So the pipeline contains only 2 stages, and we can just run the model. So let's say summarizer clinical JSL. And as we are using right now licensed healthcare models, we are using the clinical model. So to do that, we need to have access to clinical models that you can get through a license for healthcare NLP. Then we have a few parameters to control the output of your model. So let's say we don't want to generate more text than 512, and then we can also set the maximum text length to that, and we can extract the summary. So we can give a patient information. So we have a description of what happens to the patient. So let's say it's a 78 years old female, and it was taken medication and so on. So we can have all of that information from the text, and we can make a summary of that using our model. So the model says 78 years old female with hypertension, syncope, and spinal stenosis returns for recheck. So this is probably what is written here in the text, and then it says she denies chest pain, palpitation, and so on, and she uses multiple medications and has Elocon cream and Sinalair cream for rash. So this is a summary of all of this text that we can find in many patient documents. So let's say a discharge summary or a discharge note or any other type of document. So we want to have a summary of that so we can either process it in our pipeline or have it easier to understand patient information with the summary. So the same on how to use LLM loader. As I mentioned before, LLM loader, we don't need to create the pipeline. We just load them a pre-trained model. So let's say this is a quantized 8 model. So it is already smaller than the original version, and then we can just load it. And the same way as we do for large language models in other ecosystems, we give a prompt and then we ask the answer from the model. So we're just passing the prompt like this, for example, and then we can just ask the model whatever we asked in the prompt. So here we are giving the model a text, and we are asking what age group is most susceptible to breast cancer. So the model was trained on healthcare research papers, so he has internal knowledge about healthcare, and he will try to answer this question. So this is a text and say several risk factors can increase your likelihood of developing breast cancer, and then you have all of that. And then you have here some indications of what kind of age you have, and then the model was able to find that and say it was mentioned in the text is a woman over the age of 50. If it was not present in the text, maybe the model will try to answer that based on internal knowledge. So you can use it in the same way as you may be doing that in ChatGPT or other LLM. So you can just pass the prompt and ask the model to answer it. So the next application is how to create RAG applications using our models. So we can connect to other ecosystems such as LangChain. We can create a vector DB. We can connect to that, and then we can try to retrieve documents from that vector DB, and then we can use any large language model to answer questions based on that. So what I will do now is, since I'm already running out of RAM memory, I will restart my session just to free the memory, and then I need to set up the Spark session again. I have here an OpenAI key. Then I can just start the session again. And then we can start working on this one. So the idea of RAG, if you're not familiar, is that we will use embedding models to represent texts using those vectors, and then we store them in a vector database. So we will try to find relevant documents using vector similarity in a way, so that when you make a question, you try to find similar documents in your database, retrieve them from your database to add as context to your prompt, and then pass your prompt through a large language model to get the answer. So this architecture was created to avoid hallucinations, as many large language models, including those very big ones like ChatGPT, they were creating information that is not correct, and this was given the name hallucinations, so that the model was just giving you bad answers. So in a way to avoid that is to give better context. So as a way to make your prompt containing relevant information for your model, you try to retrieve from your own database. So let's say you're asking about diabetes, so you want to find documents that talk about diabetes, so you extract that, add them as context, and pass over your large language model. So let's download a few diabetes related text files, and then let's create all of that in our as a vector DB. So we will just read the text files using Spark. Then we will add a few metadata information for that, for file name, for example, and then we can just see what we have as a Spark data frame. We will have a few columns, and then we will have a few documents. So let's see how many documents we have, and we have a few file names that were read by that. So we have 1,000 documents in this example. So the first thing that we can do is, those texts can be quite big, and as you know, models, they have a limit on how many tokens they can process. More than that, they will truncate your text, so you may lose relevant information. To avoid that, what can be done is, let's split the documents, let's say with a size of 100, and then we can overlap 10 characters in the text. Then we can split that into lots of different chunks of text, and then we will use embeddings on those instead of using in very big text that will lose information. So this is what we are going to do. So we use the document character text splitter. We will split in chunk size of 100, and then we overlap by 10, and then we explode the split so that one row in our data frame will be one chunk of that. So let's apply that transformation to our data frame, and then we can check that we also are sending the data frame back to a pandas data frame, so we are getting out of Spark at this time. So here you can see we have all of that. And from each of those documents, we got different texts and so on. So what we're going to do, I see here I limited to 100 documents only. So it's not running on 1000 anymore. We are just running on 100, and then we split into 391 chunks. So this is the data we are going to use. Then we can just load the document in LangChain. So I'm not going to go over details, but we are going to use a data frame loader as we have a data frame in our data. So we are going just to load it. Now we are in LangChain. So if you are not familiar with LangChain, you can go over the documentation of LangChain and see what we are doing. But basically, we are just creating a representation useful for LangChain. So we are just adding the same texts, the same chunks into LangChain. Now, this is the connector that we have. We can use embedding retrieval, for example, that can be used inside LangChain, but using models that are in Spark NLP. So we can just download this model, and we have our embedding model, let's say. I don't know if I will get an error because I don't have GPU, but let's see what happens in this moment. I think I set hardware as GPU. So if it doesn't work, we change it to CPU. Let's see. Usually to speed up the computation of your embeddings and others, it would be much better to have a GPU available. So the model is being downloaded, and so you see it's not a very big model. We can test it in a sentence. We can just give any text and ask the model to represent that in vector. So this is the vector that you can get, let's say for one sentence. So each different embedding model have different dimension. So what we can do next is let's create a vector DB. So this is just one way of doing it. We are going to keep it in memory. So we can download it. As you can see, it can take up to 2 minutes just to create that. So maybe I will not run this, but this is how you can do. You just create a vector DB, again, using LangChain, and then from documents. So we already have the documents that we created above, and then we can send which embedding model to use. So it will use this embedding model to create the representations for all of the documents in this data frame or in this list of document objects from LangChain. And then we can set our vector DB as retriever. So this is also a way of LangChain on how to create that for RAG applications. So we can just say every time I query the database for documents, let's return the top 3, in this case, documents that are the most similar to what I asked for. So let's say we can search the vector DB for causes of diabetes, and then it will get 3 most similar or 3 most relevant documents for that query, and we can check them as well to see what is the information present in the documents, and then we can create our a generation part, right? So RAG is retrieval augmented generation. So let's generate text. We can use, for example, a GPT model. So right now we can use the chat GPT, the OpenAI object from LangChain. I already set the OpenAI API key, so I can just send it over here. We can set temperature of the model as well. Then we can just give a prompt and ask for the answer. So we can prompt causes of diabetes. It will try to get the documents from the vector DB and then try to create the answer based on that. So you can see the model tries to answer. It was given those 3 documents as context, and then based on that, this is the answer that the model came up with. Yep, and this is how you can do it. You can also check metadata information in the documents to see in which document what is the file name of the document and any other information that you added to that. So this is one way of doing the RAG application, for example. If you can apply that, you can use models that we have in Models Hub. Very quickly, I want to go over a few other things. It is that using multimodal pipelines. So I'm going to go a little bit quicker this time because also the models are bigger and it takes time to run them. But we can see what is the how to run them for a few examples on audio, image, and so on. So let's say, for example, we have 3 different types of multimodal pipelines in Spark NLP. One is for tabular data, one is for audio, and one is for image. So we have a few different types of models for all of those. And then we can check more in detail in the notebooks on how to use them. Of course, in image, we also have visual NLP, which is also a licensed library that is specialized on image computer vision tasks. So we can also see how to use it. So for visual NLP, as I mentioned, the interesting thing is that it works on top of Spark. So we have all the capabilities of Spark, and then on top of that, we built the solutions for different types of visual tasks. So we may have skew correction, image denoising, and so on. We can work on different types of documents like scanned, PDF, or DICOM, which is a type of images in healthcare, or JPEG or PNG images, documents from Microsoft Word or Microsoft PowerPoint, and so on. So we can apply many different models on top of that. So let's see a few examples. The first one will be, let's open it in Collab, for audio. So I'm going to go a little bit faster on those. But basically, we have 3 different types of models. And the most recent one, which is achieving higher performance, is the Whisper from OpenAI. And before that, we also have Wave2Vec and Hubert types of models. So for that, we will need to read audio data. So one library that can help us with that is libRosa, that can read audio data and then standardize the data in specific dimensions. So let's see how it's done. So in our example, we will get a clinical document. So this document is synthetic data, it's not real data, and it is a talk between a doctor and a patient. So the doctor is asking, what do you have? And the patient describes the symptoms and so on. So we want to extract that information from the audio and transform it into text, so that if we want, we can apply any other text model on top of that. So the models, they work on clips of 30 seconds. So the first thing to do is we have a sampling rate of 16,000, for example, that we can read this audio, and then we can use that to create 21 clips of 30 seconds each. in this example. And then we can select a few ones just for experimentation. We will need to create a struct to pass that to Spark. So what we want is the audio content, which is a big vector of numbers, and then we have a sampling rate just to keep this information in the data. The pipeline is like this. We have audio assembler. This time, the audio assembler will create a notation object from the audio content, and then we have a speech to text stage. Let's say we use Whisper. We can get a pre-trained Whisper model. It is trained for English and trained on very big data sets. Then we can just apply the model to the audio, and then we can see what the model outputs as text. So you will try to understand the audio and then transcribe it into text. So this is just how to put it back together. After we split into clips, we can just see that, okay, what brought you today? I'm just having a lot of chest pain. So, okay, I thought I should get it checked out. Okay, and then we can see the dialogue between the doctor and the patient. So pay attention that the model is not distinguishing who is talking, it's just extracting it to text. So this model can perform quite well in this time. So this is what I wanted to show about audio multimodal pipelines. So extracting text, and then since you have that, you can add, for example, named entity recognition. You can identify a few entities. You can check other types of models. Let's say you can classify it. You can apply anything on top of that. And the second thing that I wanted to show is a very brief introduction to visual NLP. So I will also go over a little bit quick because we're running out of time. But the idea is the same, but when you install the library, you need to send the parameter visual equal to true. So of course, you need to have your license for visual NLP library. So it will install visual NLP, also called Spark OCR, to your computer. Then when you start the Spark session, you also have to use visual equal to true so that it will load everything from visual NLP. It is by default set to false because it's quite heavy. So if you're not applying visual NLP models, you don't need to load it. So here I will just show a few transformations that you can apply to documents. So we can pre-process images, we can adjust, make improvements in the image quality so that we can improve output of an OCR engine. So we can also support different languages to apply OCR in different documents that comes in different languages. We can find and extract tables. We can recognize and highlight entities directly in PDF documents. So we don't need to apply OCR, find the entities, and then go back to the document. We can do that, but we can also highlight entities directly in the document. So let's see a few examples. So here we have this receipt. You can see somebody went to Starbucks. Okay, he bought some coffee, and that's it. This is the price and so on. So the first thing, we can apply transformations to the image. So this is one transformation, erosion. You will just, you see, highlight or make it the contrast different, so that when you use it, maybe the OCR will be better to extract the words out of it. So you can see it applies some transformation on it. But there are other types of transformation. We can try to remove objects. So let's say all of those small dots that we may have in the document, we can try to remove them. So you can see if the dot is big enough, it will be kept in the image. But if the dots are very small, we try to remove them from the image because we think that they are noise or they are just bad scanning. So we can try to remove them. We can also find regions in the document. So let's say we have a document and we want to find special regions. So, okay, we can find this is a region, this contains the title, or maybe this is another region in the document, and this is another region, and so on. We can just put boxes to say this document has different sections or different parts of it, and we can try to identify them. So this is called layout analysis. So we can try to find where information is being kept in the document. The next one is signatures and handwritten information. So let's say we have a document that with signatures in it, and what we are going to do is, okay, let's draw and try to find handwritten and signatures information in the document. So this is one box that we found. So this is handwritten information. This is handwritten information. It was identified, and then we can find all of that signatures in the document. So if you have, let's say, want to know if the document is signed, you can use this type of document to filter signed and unsigned documents for processing. The next example is to get a table and then extract it to text. So let's say we have one table. We previously identified the table and extracted it. Now we want to extract it to text. So we can just apply PDF to text table, and then it will transform it into a Spark data frame, and we can extract it with small transformations on it. We can get the full table just with simple transformations in the data frame. And finally, one application that I want to give before, sorry, I'm taking too much of your time, but let's say we have a chart. What we're going to do is extract this chart from this document. So we are going to use a specific model. We find the layout, check that there is a chart in it, and then we are going to use a specific model trained to find those charts, and then we will split the document by region, and then we get a chart to text annotator. So this will get the chart information and will transform it in a text representation of that. So this is what the model does. So we can see that we found the chart in this page, and then we will extract it to text. So this is the text that we get using the model. And then we can send this information to a large language model, let's say, and we can ask questions about this chart. So let's say we use a Llama model that we can build our pipeline, and then we send a prompt and say, okay, this is a chart information, and then please answer the question, and you can just query it and find the answer. So the output is just this. Okay, the chart shows average change in vitamin D levels over time. So this is what the chart information contains, and then we can ask questions about it using large language models. So yes, this part I had to go over very quickly, but I would not be now here answering questions that you may have written, and we will make a pause until the next session. Thank you.